Now we're going to do Unit 4. I've split Unit 4 up into two parts. One is just basically an introduction to the Earth systems, the geosphere, which is basically soil characteristics and formation, the atmosphere, and the hydrosphere. And then the second part, which will be the second lecture, I'll split it up into two, will be on the interactions of all those and how it impacts climate. So let's dive in. Plate tectonics is the first part, which is how the Earth's crust interact. So Earth is layered. It's not just like a blob of Earth. The innermost part is the core, followed by the mesosphere, the asthenosphere, and the upper part is the lithosphere. That's where we are. It's the crust. Generally, plates are less dense, and they're being pushed around by the lower parts of the Earth. So a lot of our plate dynamics is based on what's happening underneath the Earth. So where these plates, so the Earth isn't just like a solid plate. There's all these, it's basically like a puzzle piece, but the individual puzzle pieces are moving around all independently of each other. So where these plates, if you think of like if you had a ball and you cracked it, or you had a vase and you cracked it, and then all those plates are moving, all those cracked parts are moving around. And so what's happening at the edges of those plates is what forms a lot of our geology and our geologic events. So where those plates are interacting, you have high geologic activity. So if the plates are coming together, we call that a convergent plate zone. One generally is going to be subducted under the other. That's called a subduction zone, or they can just crash into each other and you get a mountain formation. So if you have one plate moving under the other, one of the plates is going to melt, which forms volcanoes. It can form mountain chains also. You also get some earthquakes, although not as many as you get from transform or strike slip boundaries. You still get earthquakes because it causes pressure to have one plate moving underneath the other. And you have a release of magma, which melts and is what forms volcanoes. So that's what happens there. If your plates are moving away from each other, that's called a divergent plate boundary. They're moving away. In those areas, you can see it, here they're spreading apart. You end up with, that's how you form ocean spreading. You can get seafloor ridges. The mantle from the asthenosphere pushes up through the lithosphere. Generally, you don't get as many earthquakes here. You just get a lot of magma flowing up. But it is possible. Wherever these plates are moving, it's high friction area. And then the last one we're going to talk about is a strike slip boundary or a transform boundary. And that's where the plates are sliding past each other. They're more like grinding past each other. And you have tons of friction building up from them grinding against each other. You don't have the formation of ridges like you see in divergent plate boundaries. You don't have the formation of volcanoes like what you see in convergent plate boundaries. Instead, you get a lot of earthquake activity occurring at those fault lines, at the places where those plates are sliding past each other. So here I have a quick little diagram. If you want more time with this, I believe it is in your notes in OneNote. Look at my section 4.1 notes and you'll see them there. You see a lot of plate boundaries. It's called the Ring of Fire, which is the outline of the Pacific Plate. And it has all the different types of plate boundaries there. So you end up with all those different geologic events happening there. Okay, so how does soil form? Soil is formed when a parent material is weathered, either chemically or physically, and then transported and deposited somewhere else. So what can impact? So think about primary succession. We have lava flow over the soil, creating bare, hard rock. And how does that bare, hard rock become soil? Well, through chemical and physical weathering, which is what we're talking about here. So what impacts how fast that parent material, that rock, is broken down? Well, the type of material that it's made of. The soil maintains the chemistry from its parent material. So depending on what that parent material is made of, you're going to have different ways that the soil will form. The climate, generally the hotter it is, the faster it'll happen. The amount of wind and rain will impact weathering. Higher winds, higher rains will impact weathering rates, and the amount of leaching that happens as well. that all impacts leaching. Topography, the greater the slope, the greater the erosion rates. Think about a slope with soil. That soil will move right down the slope, and so you see the same thing here, that if you have a lot of wind and rain on a slope, you're going to have increased weathering, so the rock will break down faster. Certainly plants and animals help break down that rock, and time. This is an ongoing process. No matter where you are in succession, your soil is still being formed and still being impacted by weathering. So we can split up these soil layers called a soil profile. In fact, if you were to take an auger, which is it's a cylinder tube that you can put into the soil, and you were to move it down in your backyard, maybe you did this before our soil lab. If you have questions about anything that I'm talking about in this lecture, I would refer right back to that soil lab. Remember, Mr. Siflinger came in and hung out with us as we analyzed his soil. So you take your auger down and you'll be able to pull up these layers. The R layer, which is your hard bedrock. This is unaltered. It is still in the process of being weathered. C, which is your partially weathered rock, or your substrata. It's mostly made up of parent material. B is your subsoil. We have accumulated our fine materials and mineral precipitates. Between A and B is a thin zone called the E zone, where you have a lot of leaching going on. And then A is your surface horizon, where it's usually darker. You have high content of organic matter. And then your O is your organic horizon. And this is mostly made up of a combination of decomposed and non-decomposed materials. You have a lot of humus in this layer. That is your O layer. So we see these patterns consistent. But of course, like different habitats, if you have different surface soil, you're gonna different bedrock parent material, you're gonna have different layers. It's gonna look different depending on where you are. And there are people who categorize your soil layers and are able to differentiate and can tell you where you are based on your soil layers and what's in each of them. Kind of cool stuff. So we talked a lot about this, how soil erodes over time. Water can run that soil into waterways, wind, gravity, topography. And then humans also can impact soil erosion over time. We talked a lot about farming and farming techniques that increase soil erosion. Deforestation, whenever you cut down trees, those roots are holding your soil in place. So deforesting can increase soil erosion rates. And then tilling, which we talked about also in Unit 5, turns soil over and it can then be easily eroded off. So there's 3 big types of soil erosion. Sheet erosion, when the entire surface of that soil is removed. A really easy solution to this is just maintaining plant cover. We see sheet erosion a lot when we do like slash and burn, and then that whole sheet will remove. Just keep it covered with some plant material. Crop rotation, think about things we talked about in Unit 5 here for methods of soil conservation. You'll see that really is specifically for sheet erosion. Rill erosion is when small channels of water form on your plot of land, and what really helps prevent rill erosion is strip cropping and contour plowing, all methods that we talked about in Unit 5 for soil conservation. And then finally, gully erosion, which is really a subset of rill erosion. Rill erosion is our umbrella term, and gully erosion is a type of rill erosion, where basically that rill becomes wider, and so really at this point you can't plant to fix it. You have to start really diverting water away from your rills. Okay. Soil composition and properties. So soil texture, there's 3 soil textures. They are clay, sand, clay, silt, and sand. And a soil texture is based on size. So sand is the smallest particle, silt is the middle, and clay is the biggest particle. And generally your soils aren't going to be made up of just one soil texture. Your soil is going to be a combination of the 3 different types of texture. And how they all come together is going to determine what properties you see. So all of your different soils, your sand, silt, and clay, that size is going to determine how much water can pass through. So our big properties that we see water holding capacity, permeability, porosity are all impacted by size. And then soil composition is the percentages that your soil is of each of those textures, and then that combination will determine your soil properties overall. The atmosphere of the earth, that was a big switch from the soil to the earth, but we're going to do it. The earth is composed mostly of nitrogen gas, N2. We talked about the nitrogen cycle, breaking up that N2 by bacteria or by the Haber-Bosch process to make the nitrogen available to plants. But most of our troposphere gas is made up of nitrogen gas. Oxygen is second with 21%, followed by our trace elements. So we have the troposphere, which is basically the lowest atmospheric layer. It's what we're in currently, followed by the stratosphere. That's where our ozone is. When ozone ends up in our troposphere, that's called tropospheric ozone, and that is an air pollutant. We will talk about that in Unit 7. Followed by the mesosphere and then the exosphere. So the atmosphere, those layers and all the gases that are in each layer are held in place by gravity, and the atmosphere moves from two things. One, convection cells, which are heating and cooling of the air in these cyclical manners. So hot air rises, and as it rises, it thins out. It increases in density and cools. It condenses and falls. And so that cycle just continually looping around over the surface of the earth. We have our Hadley cell, our Ferrel cell, and our polar cell, but they're all following these convection cells over the earth. And then we also have the Coriolis effect, which is caused by the turning of the earth. So because the air is a globe, it's an orb, and it's moving in space, basically the air that is rising in that Hadley cell is also turning at the same time. It's curving because it has to move. It's moving at a different rate depending on where on the globe it is. So at this equator, it's moving at this rate, and then at the poles, it's moving at a slower rate. So it has to curve up. So the convection cells and the Coriolis effect come together to basically create these predictable wind patterns and predictable climates. So between 0 and 30 north and 0 and 30 south, the trade winds are the winds that really are prolific here, and it's warm and not as windy. Our westerlies are between 30 north and 60 north and 30 south and 60 south. And then our easterlies are between 60 north and 90 north, which is our North Pole, and 60 south and 90 degrees south. And we see generally it's very windy and very cold. Whenever you move from the equator to the pole, you're going to decrease temperature. Now let's talk a little about the hydrosphere, which are going to be our watersheds and our river dynamics. So rivers flow with gravity from the highest point to the lowest point. So the watershed is basically your high point all the way to the low point, and rainwater takes rain with it from the high point to the low point. So it can move through the watershed on top of the water, but also it can percolate into the ground, restoring our aquifer and our groundwater. So we can characterize a watershed by how big it is, by what plants are there, by the type of soil that it's in, and the slope. So if we think about like a watershed off the Great Divide in Colorado, and compare that to our watershed here in the Everglades, where it's very flat, we can compare all of these things. The watersheds are very impacted by humans. A lot of it from that groundwater percolation. Whenever we pave areas for urban areas or suburban areas, we prevent water from percolating back down into our groundwater. That's I think one of the biggest ways. Logging, whenever we cut down trees and we remove those roots, the rain will rush into the river faster. We're increasing turbidity because a lot of that soil is ending up in the river. We're increasing soil erosion also, which you guys said is something that a theme that we have been talking about a lot. Soil erosion, soil erosion, soil erosion. Anything that you do in the urban area, pesticides, fertilizers, leaks in cars that are releasing gasoline into the streets, all of that is going to move into your watershed when it rains. Industrial waste and industrial pollution can end up in your river when it rains. I already talked about impermeable surfaces. Livestock and cropland, we've talked a lot about in Unit 5. We talked a lot about cows, cattle, CAFOs, and free-range grazing. Also, all of that waste ends up in our waterways. And then dams, it's almost like the opposite, but still with devastating effects. You're preventing the river from flowing. So you're blocking your flow of sediment, but your nutrients that are necessary downstream aren't getting there. So you're ending up with greater levels of pollution and nutrients in one part of the stream and then nothing in the second part. Okay, that is it with part A. We will start with part B the next lecture. See you then.